Hi, in this video, we are going to discuss about resource constrained system design. So, whenever we want to deploy an IoT device into the field, immediately we have all these limitations or problems. So, we cannot attach a very high capacity battery. So, we'll always have a limited battery. We will be having a very small memory and very low processing power, and you can this is an IoT device which has a small battery, small RAM, and a small processor. So this device has to function in the expected manner, even within these limitations. So this has to work like an efficient and a lightweight. We have to have a very efficient and lightweight system design, so that we are still able to, the device is still able to run within these limitations. So coming to this, we already have low power microcontrollers. So low power microcontrollers means these microcontrollers are going to consume a very less power. So we already have microcontrollers like ARM Cortex M board and the ESP32 board. These boards will consume only very less power, and and they also have a lot of functionalities. For example, the ESP32 board has a Wi-Fi enablement, so you can actually transfer the sensor values across a Wi-Fi and log it to a cloud using the ESP32 board. And you must be familiar with the fitness band, which will run for months on a small battery. So these kinds of devices are enabled with these low power microcontrollers. Then only they will, they will be lasting for weeks or months on a small battery. Now, coming to the memory optimization techniques or the power that is consumed, we have different techniques available for memory optimization. One of them is buffering. So, what do you mean by buffering? So, when you have a lot of data coming in, and you want to send this data through a communication channel, suppose I have deployed some 100 temperature sensors. So I'll have T1, T2, etc., T100, these many values coming from the field. So I can either transmit them as they arrive. So in that case, I'll transmit T1 when it arrives, and I'll be transmitting T2, and so on. So, but then the problem there is that I'm just keeping on transmitting the values as and when they arrive. So the idea is, I mean, I'll be using the communication network. Communication network will be always enabled, and it has to work. Even though the data is uh, very small compared to its bandwidth, it will be enabled throughout. So we can actually do something better. That is, we can buffer it. Okay, so what we can do is we can buffer all the temperature values, say from T1 till T10. So maybe I can buffer from T1 to T10 in a small memory, so which is attached here. And then once 10 values arrives, I'll communicate this across the network, and then I'll wait for the next 10 values, say from T11 to T20. And then once those arrives, I'll send that packet across the network. So this way I have a very small memory, which is enough to fetch and save these 10 values, and then transmit it whenever it is needed, so utilizing the full bandwidth of the network. So this can be termed as buffering, and this is kind of an optimization technique which will allow us to store the small values in intervals, and then transmit it all at once based on the bandwidth of the communication channel. Now, coming to data compression. So whenever you want to transfer something, think about whether you want to transfer the entire data. For example, if I have 100 packets to be transmitted. And if I can compress this 100 packets into a single packet, then the transmission will be more smoother. And then in the receiving end, if I can have the provision of converting this one packet, if required, into back into the 100 packets if required. So now, how is this possible? Data compression. One small example which I can tell you is that, suppose you want to transmit a data, okay, which is containing, uh, let's say character C. Say suppose it goes 100 times. So instead of transmitting this particular string, uh, containing C, for 100 times, I can say C comma 100. Okay, and it can be interpreted as C 100 times. So this entire string is now pretty much reduced to C comma 100, and it can be interpreted back to, it can be uncompressed also in the receiver's end if it is required. So this is a very small level, a very high level explanation of what is a data compression. Now, another technique, this for optimization of memory usage is to use efficient data structures. For example, in this example, you can see that you have a matrix here. So the matrix gets only very few entries in this matrix are enabled. You can see a one in very few places. So if you know in upfront that the matrix is going to be very sparse, then you need not store the data in a matrix format. Okay. So before that, data structures is all about storing the data and accessing it in a easy manner. So uh, whenever you have the requirement to store data, you have different data structures available to store the data in the form of lists or arrays, or you can store it in linked lists. So all these options are available, which you will be studying in your next semester courses, especially in the data structure course. So here I'm telling about a scenario where I'm storing the data in a 2D matrix, two-dimensional matrix, where if I know in upfront that this data will contain only very few ones, I need not store it in a matrix, and instead I can store the locations of these ones in a list. Like this location is 1 3, and this location is 2 3, and this location is 3 1. So instead of storing all these 4 into 4 entries, I can just store 3 entries. So this is a very simple example of making use of an efficient data structure. So in this particular scenario, keeping this list, we have the choice of either having a list or having a 2D matrix. Okay. But then here we identify that only very few elements in the 2D matrix is going to be enabled at the same time. So we can make use of the list in this case. So this is all about memory optimization techniques, and we'll stop here and we'll discuss some of the low power protocols in the next video.